Hello, everyone. Hi, I'm Nico Strom. I'm a principal scientist in the Alexa group at Amazon. I'm here with Arpit Gupta, a colleague of mine, to talk about deep learning in Alexa. It's a pretty good turnout. Thanks for coming. I know you have options. Anyway, so this presentation, this session will pick up roughly where Rohit Prasad ended earlier today in his State of the Union. He made lots of references to deep learning in Alexa, and we'll go one step further in this talk. It won't be a deeply technical talk, but I'll talk about some of the history of deep learning. How did we get here? In particular, in the sense with the lens of speech recognition and speech technologies. And then I'll start talking about what we're actually doing for Alexa and how we're making it better using deep learning. And then Arpit is going to take it home by talking about the special challenges we have with the skills kit, where we have thousands of developers writing their own apps, and how we are solving some of those challenges with machine learning and deep learning. So this is the outline that I was just mentioning. OK. So I'll start with some of the history of deep learning, and I'll cover this time period from mid-'80s to today. And this happens to be also kind of the history of my own career. So please forgive me. I will sometimes talk about what I did during this period. It's not like I'm trying to make this all about me, but I can't stop myself. I'm sorry about that. So in 1986, Hinton, Rumelholt, and Williams invented this thing called the backpropagation training algorithm. And that is a machine learning algorithm for training artificial neural networks. And that set off a lot of activity in the 80s and 90s, fundamental research on how to train these neural networks. And on the other side, I'm going to bookend this by Amazon Echo, launched in 2014. And that's in a completely different era where machine learning and deep learning, you can read about it in the press, and it's another period of great hype for deep learning and machine learning. In between, though, it's interesting. Some people call this the neural winter. So there's this period of 10 to 12 years in here where there wasn't as much activity. So a lot of this history talk that I'm going to give to you is about why did this happen? Why is there this sort of camel hump shape of activity in this field? So let's go back to the beginning. So the algorithm that they invented was a machine learning algorithm for training this type of model, this type of mathematical model using data. So you have some input, which can be speech or images or whatever, and then you have some output. You know what the correct output is supposed to be, and you have lots of data to train this model. So they invented this backpropagation algorithm, which then set everything off. An interesting thing about this one, though, is back then in the 80s, it was really popular to visualize neural networks in this particular way. It evokes an image of neurons and connections between neurons and so on. So that was sort of the inspiration for neural networks. These days, we don't really do that. We use block diagrams or just a mathematical formulas. All right. So we have the Echo still there. Here are some of the more recent milestones I'm sure you've read about in the press. The AlphaGo that beat the Go world champion, milestone in reinforcement learning using deep learning, and of course the great improvements in object recognition that we've seen in computer vision. Now in my field, in 2010 and 2011, both Microsoft first and then Google demonstrated really breakthrough speech recognition accuracy improvements, though, on large vocabulary speech recognition, which is what we need for Echo. I was actually working at Microsoft at the time, and I can tell you it was a really exciting time to be working on speech recognition. Speech recognition used to be this field where you fought really hard to get just small accuracy gains year over year, maybe 5%, maybe 10%. But but this, in one swoop, you got like 25 to 30% accuracy improvements in just by applying this technology. And it also had the side effects of simplifying the systems a lot. So if you've been wondering, why speech has become such a hot area for user interfaces, a large part of it is actually that speech recognition got a lot better the last few years. Moving back in time a little bit, there were some precursors to this kind of boom in deep learning. In 2002, Salahuddinov and Hinton discovered a way to train much deeper neural networks than we had been able to train before. And that was an important prerequisite for these models. And later, Hinton and his team, in 2009, they actually demonstrated speech recognition accuracy on a much smaller task, but they kind of led the way for Microsoft and Google's breakthroughs later. Going back to before this neural winter, there were a lot of fundamental research. LeCun et al. Published how to use convolutional neural networks for computer vision, and Schmidt, Huber, and Hochreiter invented the LSTM architecture for recurrent network, which is super important for speech and language applications. So between that and the backpropagation learning, the foundation for deep learning were already laid in the 80s and the 90s. All right, so I'm going to zoom in on just the speech recognition part for a little bit. So the two bubbles are from the previous slide are still here. That's what's happening today, and we have the echo still there. But it's interesting. Speech recognition was actually one of the first applications of artificial neural networks. Already in '89, Alex Weibel and his team published the time delay neural network architecture, which is very similar to the neural networks we're using today for speech recognition. A few years later, Tony Robinson demonstrated how to use the recurrent networks for speech recognition, and he got very good results. And here's one of those. A year later, I combined these two techniques to a combined architecture called time delay recurrent neural networks. And the same year, Morgan, Borlard, and others showed how to use context-dependent models. And this is kind of technical, but is a very, very important aspect of high-performing speech recognition. You have to take into account the co-articulation, right? The phonemes, the speech sound, they sound differently depending on what other sounds are around them. So what they did was they incorporated that into their neural networks. And finally, again, myself, I introduced speaker vectors for speaker adaptation in '96, which is a precursor for the speaker adaptation that's done in neural networks for speech recognition today using I-vectors. So again, what you see here is that there are these two periods of great activity before and after this neural winter. And it's interesting to think about why did this happen. And several explanations have been put forward, and I think they're probably all true to some degree. But so one is the impact of how much data do you have. In speech recognition, we measure the amount of training data for our neural network. We measure that in hours of speech that we recorded, and we painstakingly labeled with the correct phonemes for each recording. So if you're in the US, if you're 16 years old, then you get to drive one of these, right? That's about 140,000 hours. Now, you're not listening to speech all the time. Maybe 10%, you're sleeping and other things. So maybe 10% of the time you actually hear speech. So by the time you're 16, you've heard about 14,000 hours of speech, give or take, right? So that's just to ground you, to give you a sense for these numbers. A 16-year-old might have heard, they have training data for their internal speech understanding of 14,000 hours. So here is how our corpus sizes have grown over time. I don't know exactly, but 1986, it was probably less than 10 hours of data that they used to train their speech recognition models. At the beginning of this so-called neural winter, the training data was around low hundreds of hours. And at the end, it was more like low thousands of hours. And today, of course, we use even more data to train our speech recognizer. But what you can see here is that there's a tenfold, there's an order of magnitude increase of the amount of data that we used. So that is one important aspect. Another one is compute. So how fast can we train these models? In 1986, I don't know exactly what an individual scientist would be using, but there were supercomputers around that could get 1 gigaflop. And in the beginning, at the beginning of the neural winter, roughly, you could get a workstation that has 1 gigaflops on your own desk. So that's a little bit better. At the end of this period, this is when the GPU era started, and you could get 350 gigaflops in your workstation. So that's already 2 orders of magnitude increase. And this is around the same time that AWS started offering instances with GPUs as well. Of course, today you can get a P2 instance with up to 70 teraflops of single precision. So again, 2 orders of magnitude more compute, that made a difference too. But the last one I think is the most interesting one. So during this neural winter period, MapReduce was the dominant way to do distributed computations. And in particular, the expectation maximization algorithm is very well suited for that. So techniques that use that worked really well during this period. And typically, because training neural networks doesn't really work well with that, so you would train a neural network on just one host. So it didn't scale. And one thing that we've learned also after this neural winter period is we've started to learn how to scale it out, how to distribute neural network training across many hosts. And so there's this well-known paper by Dean in 2012, and there's another paper by myself in 2015 about how we do this at Alexa. And so that is the thing that gets us going and gets us to scale this further. Let me see. All right, so I'm just going to conclude my little brief history lesson here with, so in the 80s and 90s, lots of fundamental theory, algorithm design, research, and then in the decades after, we got orders of magnitude more data, orders of magnitude more computational capacity, and there were a few key algorithmic inventions that enabled us to train deeper networks. And then finally, what lets us keep scaling this up is the rise of distributed training for neural networks. All right, that concludes my little history lesson. And now I will talk about what we're actually doing at Alexa. So I'll take speech recognition as an example again. So we have thousands of hours of speech that we've recorded, and we have the ground truth. We know what people actually said, and we store them on S3. And we train the networks using a distributed training of GPUs on the EC2 cloud. Now, the reason that the MapReduced methods don't really work well for distributed training of neural networks is the way it works is that the nodes really need to communicate updates to the model, the updates to the neural network. They need to communicate that very frequently. So what happens is that you very quickly you get to an I/O bottleneck. So and you can't speed things up anymore by adding more nodes. The way to think about this is that GPUs compute these updates to the network very fast. So you can think about there are several updates every second, and each update is about the same size as the model itself. So nominally, it's hundreds of megabytes that each of these workers will have to communicate with all the other workers many times per second. So that doesn't really work well. And so the solution that we came up with at Alexa was to, using a couple of different approximations, we can reduce the size of these updates. We can compress it by at least 3 orders of magnitude. And that's what helped us make this work. Here's a graph from that paper from last year. It shows how the speed of the training grows when you add more and more workers. And so you can see that the speed grows almost linearly up to about 40 GPUs. And this was with the older, because this is last year, this was with the G2.2 type GPUs. And then it slows down a little bit up to 80 nodes, but it's still almost linear. One thing that's interesting to note on this is that, well, the y-axis, you probably don't really know what that means, but it's frames per second, and there's 100 frames each second of the recorded speech. So what it means is that if you look to the right for the 80 workers, 550,000 frames per second corresponds to about 90 minutes of recorded speech that we're training on. So what this means is that every second, we can process 90 minutes of speech. And so, well, that's another one. That's another one of our superpowers, I guess, because you know, the 16-year-old has nothing on this, because it would take them 16 years to accumulate 14,000 hours, and with this system, we can do it in a couple of hours. So that's our sort of our general deep learning infrastructure. I'm going to move on to I'm going to move on to the first technology example, which is speech recognition, which is the most obvious thing that the Alexa and Echo does. So first I'll show you just the basic building blocks of a speech recognition system. You have your signal processing. First you have your sound. So it comes from the microphone, and then you do some signal processing on it, convert it to the frequency domain, and so on. And out of that comes, every 10 milliseconds of speech, comes what we call a feature vector. It's a vector of numbers. And that feature vector is fed into the acoustic model. And the acoustic model is the thing that does the classification from audio to phonemes. So out of the phonemes comes, every 10 milliseconds comes a prediction of which phonetic sound is this. Next up is the decoder, which is the thing that does this huge search over all the possibilities, all the words, all the phonemes, and what are the most likely sequences of words and phonemes, i.e. the grammar. But it's a probabilistic system, so what you get out of this is the most likely words that the user said. So in this case, maybe it's a thermostat command, increase to 70 degrees. And the last step is the post-processing, which will make it look nicer, easier to read. In all of these blocks, we use machine learning and deep learning to some degree, but today I'm going to talk mostly about this block, the acoustic model. So it's a classifier. It takes a vector of numbers as input, and it spits out the probability for each of the phonetic classes. All right, so here's a stylized neural network. So you have the input at the bottom, and you have hidden layers that transform that feature vector until you get to the last layer, where it transforms it into the probabilities of the phonemes. And this is an example of the US English Alexa speech recognizer, right? So it has US English phonemes coming out. And so we've recorded thousands of hours of US English for our launch of Amazon Echo, and it was very costly. We had to also transcribe all of them, obviously, and to know the ground truth, to know what the correct results should be, so we can train the model. But of course, it doesn't end with US English. There are many other languages, and this year, for example, we've launched German. And so it would be very costly to do this for every language in the world. Now, it's interesting. An interesting thing about these neural network models is that you can do what's called transfer learning. So you remove this layer, and you keep everything else the same. So now we have a US English model, but it doesn't have the last layer. And then we add a German model. So this is our starting point for training a German model, and it's called transfer learning. And if you think about it, languages are very different, and the phonemes are all different, but there's a lot in speech that's common between all languages, and that's why this works. That's why when you initialize the model like this and train it with just much less data, just a fraction of the amount of data we trained for the US English model, you actually get a German model that works really well. So that's all I wanted to say about our speech recognition. I'm going to move on to natural language understanding. So when in Alexa, the key things in natural language understanding that we do are intent and entities. So the intent applies to the entire user request. That's just what did the user want. It's a classification. And so in this case, they wanted to play something. So it's the play music intent. And entities are sort of the arguments. So the artist is Def Leppard. The song is 2 steps behind. And so our job is to figure both those things out. So the first one is a classifier. The other one also requires that we figure out which words belong to the 2 intents. There are 2 problems with this. If you compare with the previous thing I showed you with the speech recognizer, there are 2 problems. Speech recognizer had a simple vector input, fixed size vector. Words are symbols, not vectors or numbers, so we have to do something about that. And also here, there's different numbers of words in each request, right? It's not a fixed size anymore. So the first problem with the symbols is solved with what's called word embeddings or word vectors. And what that means is that you just assign a vector to each one of your symbols or your words or your tokens. And there are different algorithms to optimize how you choose those. But here you can see an actual projection of this large space, this large dimensional space of word vectors down to 2 dimensions. So you can see that words that are sort of semantically similar are close to each other. Right? The other problem about the variable length, and this slide broke, apparently. Sorry about this. The other problem about the variable length is solved by recurrent neural networks. So a recurrent neural network retains a memory of what it has seen. So let's see if this works. It's one. Okay, it's not doing what it's supposed to do, but it's taking one word at a time as input, and then it feeds back whatever it has in its memory to itself. That's why it's called recurrent. And then when you get to the last word, and then it does that one final time, and then at that end, it outputs the result for the entire sequence. And so that's how you solve the problem with the variable length. And so we do this. I'm only showing you this for the intent here, but we do similar processing for the entities as well. All right, the last technology that I wanted to talk about how we're using in deep learning and Alexa is speech synthesis. This, by the way, is the same technology as is used in a Poly service that you might have heard about today. All right, so speech synthesis. First, let me just show you what the steps are that you have to do speech synthesis. You have to start with a text and normalize it. And if you remember, this is kind of the inverse of what we did for the last step for speech recognition, right? So now we go from that nice readable text to just the word tokens. The next step is to convert the words into the phonemes. It's called grapheme to phoneme conversion. So now you have a string of phonemes. This is the thing that we want the synthesizers to speak. And then there's the big one, is the waveform generation, going from the phonemes to the actual sound. And let's see if this works. That did not work. Anyone here from the tech team? There's supposed to be audio. No? Shall I go back?
She has $20 in her pocket.
Oh, there it is. And that's what it sounds like. Kind of silly to wait so long for that, but I'm sorry about that. All right, so the way that this is done at Alexa is with concatenative synthesis. And in concatenative synthesis, you record an actual human voice talent speaking hours and hours of human speech, and then you slice that up in small segments, and then you create a database for that. And the segments are called diphones because we slice them up such that the first part is the last half of one phoneme, and the second part is the first half of the other phoneme. So that just happens to be a good way of segmenting speech to make it sound good when you concatenate it back together. And so we pride ourselves of having really good speech synthesis for Alexa. And one thing that you really have to do well to get there is when you're recording this database, you have to be very meticulous. It's a very difficult process to master, to record these segments so that the entire database is very consistent, so that you can pick and choose segments from anywhere in the database and connect them together and have it sound well. The other important part, excuse me, the other important part is algorithmic. And that is, so once you have this database, how do you actually select the optimal sequences to stitch together to make the final waveform? And the first thing you need to do there is to figure out what the objective function is. So how do you know what's a good segment to select, and how can you search this big database for these segments? So for example, we would label the segments with lots of attributes. I'm going to talk about 3 of those attributes today. The intensity of the segment, the pitch of the speaker as she was speaking this segment, and the duration, the length of the segment. So those are some attributes that we label this database with. And when we then run this big algorithm to try to find the correct segments to concatenate, we have to look at these phonetic symbols. We have to look at what the words were. We have to look at the speech act. Was it a question or what was it? And then find the optimal target. First, we find the optimal target values for all these attributes. So we find for one of these phonemes, for example, we find what's our target for the pitch here, and what's our target for the intensity and duration here. And then once you have that, you can search the database for the best sequence of segments to stitch together and then play it. And this is where we used a recurrent network as well. So to get those targets, given the one sequence, we used a recurrent network that takes as input these phonetic features, linguistic features of the thing you want to play, and also the semantic word vectors are coming back here, the word embeddings. And then the network will spit out, here's the target pitch, duration, and intensity that I want you to play. And the next step is to try to find that in the database of diphones. So that's how we use deep learning in our synthesis as well. So this is more audio. To get the place where prosody and intonation matters more is for long form text. So it doesn't matter as much for the shorter phrases. But so I have a longer form example here, and you have to, first of all, this has to work, and then you have to listen kind of carefully because the baseline system that we had before we did this was pretty good. So this is the baseline.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
So I think that already sounds pretty good. I'm not a native speaker, so I'm from Sweden, so I don't get all the nuances, but let's see what it sounds like after and see if you can hear a difference. So listen carefully.
Over a lunch of Diet Cokes and lobster salad one balmy fall day in Boston, Joseph Martin, the genial, white-haired, former dean of Harvard Medical School, told me how many hours of pain education Harvard med students get during 4 years of medical school.
All right, so if you listen carefully, you can probably hear that it's flowing better, there's less disfluencies, and so on. So that's the sort of incremental improvement we got from that deep learning here. And this is actually all I have to say about the different technologies. Arpit is going to talk more about the Alexa Skills Kit and how we're using that, how we're using deep learning, machine learning to solve some of the challenges there.
Thank you.
Thanks.
So Alexa Skills Kit. You'll probably hear about Alexa Skills Kit a lot during reInvent, and this is just probably one another talk, but our view of how we think about Alexa Skills Kit. If I were to define Alexa Skills Kit in one sentence, I'll say Alexa Skills Kit is a bridge that connects developers and customers on Alexa. I'll briefly touch on 3 things in this talk. Why we launched Alexa Skills Kit, how to write some great skills, a few tips on that, and how we use machine learning, the same deep learning techniques that power Alexa's built-in capabilities like music, search, to also power the skills that developers build. When we launched Alexa in 2014, people loved interacting with voice, even though it came with limited capabilities like listening music on Prime or weather, and people already wanted to do more. And we launched more capabilities over the years, like shopping or searching for local businesses. But people or our customers didn't want to stop over there. They wanted to interact with all the apps that exist today on mobile phones, on Android, iOS. They wanted to play games, ask for Uber rides, order pizzas, connect their home automation devices, and experience all these different services through voice. And that's the main reason we wanted to launch Alexa Skills Kit, because unless we connect developers directly with customers, we can't develop fast and we can't innovate fast enough. Let's look at some of the numbers since we launched Alexa Skills Kit in last year. So we launched with a few hundred skills that were built in-house to early September, where we were already about 3,000 skills. And today, as Rohit also announced in the State of Union, we are past 5,000 marks. So we are pretty excited about it. Some of the big developers that have already come forward, like Uber, Domino's, Capital One, where now you can ask for your account balance on Capital One, or ask Fitbit how many calories you burnt in a day. But my personal favorite is asking for more cat facts. As we are at reInvent, I'll focus more on what ASK means for developers and how developers can interact with ASK and build great skills. So ASK is basically building a voice user interface. Just like when you develop a web app or a mobile app, if you want to take your idea to a mobile phone, you build iOS or Android app. When you want to take your idea, your service or business on Alexa or a voice platform, you build a voice user interface. The way to do it would be to provide sample utterances, examples of how people would interact with your skill, what would they say to invoke certain intents, certain slots. And once you provide these utterances, Alexa learns how people would interact with it, builds the machine learning models, deploy it so that it can be accessed at runtime instantaneously by all customers. I'm sorry if it's small for people in the back. I'll go through one example in detail. So say this slide defines the entire voice user interface. So this is all that needs to be done if you want to write a skill. At the top, we define intent schema, or the intents that you want the customer to interact with. Think of intents like specific actions that do one thing. If it were a web form, if it were a web application, think of it as a web form that does like getting users' detail or booking flight or booking a cab, but just does each intent does one specific action. Or in this example of a horoscope skill, we have an intent get horoscope, which does one thing and one thing only to inform or ask information about the horoscope. And as in web forms, we often have fields for age, name in a user profile form, or arrival, departure city in a website in a flight booking form. Similarly, we have slots in Alexa for intents. These slots serve the exact same purpose. They are there for customers to fill in some information, like fill in the information about which horoscope sign they want the horoscope for, or which date they want the horoscope for. Moving to the next part, defining slot types. Slot types are really grounding these slots even more. They are enumerating over the different possible values a customer who's interacting with your skill might say. For example, in this case, for sign, customer might say Aries, Cancer, Leo, Pisces, Virgo, and a few others. If you also see, we have an Amazon.dates slot type for the date slot. And this is one of the built-ins that Amazon provides, which is backed by much larger amount of data. Now you have defined your intent schema, your slots. So you have defined the interaction, the kind of interactions you want to have, the kind of actions the customer can have with the skill. But you still need to define what utterances, what specific utterances when said should map to which intent or which slot. This is done in the sample utterances part, where you define examples like what's the horoscope for sign, what's the horoscope for sign date. So if you take the first example, if someone says what's the horoscope for Leo, then Alexa knows that it needs to send back the get horoscope intent filled with the sign slot. Similarly, if someone says what's the horoscope for Leo today, then it knows that it needs to send in both the slots, sign and date, for the get horoscope skill, get horoscope intent. It's a tiny small diagram of all the different steps that we do during a skill building process. So once you click submit, we store your skill definition, build a model, and push it to cloud so that it's accessible instantaneously. Again, this uses numerous AWS offerings like EC2, DynamoDB, S3. To talk more specifically, we build two kinds of models, a finite state transducer machine and a machine learning or statistical model. Finite state transducers, or FSTs, are like exact match rules. They really help us to be accurate and exact on the utterances that were provided by developers, so that whatever happens, we never make any mistake on the example utterances that the developer provided. But more often than not, these are not restricted. So customer can come in and say anything and is not restricted by what the developer provided. And for those interactions, we build the statistical models which generalize much better using the same techniques Nico talked about. Let's see an example of Uber skill and where machine learning comes into play. Say Uber defined their skill with a few sample utterances to ask for a cab or ask for a ride. They can go in and specify utterances like get a car to destination and get me a car. And these would work just fine if we had built FST. Someone comes in and says, get a car to Mirage, and works 100% of the time correctly. But someone might come in and say, hey, I need a car to Starbucks. Now, since Uber never defined this utterance in their sample utterances, we need machine learning models to generalize from more data, so that even when we see an utterance like this, we know that it's asking about a car, and it wants to go to Starbucks. And when we use machine learning techniques like this, it makes interactions much more natural and the experience magical for customers. So how do we do this? How do we generalize better? And to answer, we use the same transfer learning techniques that Nico already talked about, which we use from going from US English to German model. So Alexa has already interacted with you a lot of times, and you have asked about local businesses, destinations, cities. So it knows what context people ask destinations in, what context people are asking for things like Starbucks. So when you say many more different utterances but still asking about destination, it knows how to generalize this. So as promised, I'll also give a few tips on how to write great skills. We briefly touched on what slots are. So slots are like fields in your forms, in your web forms, which provide your skill the values that the customer wanted to interact with in the intent. So while defining catalogs, provide as many examples as possible. And if, for example, say in the destination slot, you have utterances or destinations with varied length, it always helps to provide examples where in the catalog we already see examples with varied lengths, which helps us to generalize better. And as Rohit talked today in his State of the Union, we had a small library of built-in slots earlier, and today we are announcing many more, hundreds of built-ins, which are backed by a lot more data, which Amazon gathered over the years, and which really helps to generalize all these interactions better. Also, what we have noticed is where we currently are in speech technology, asking for too many slots in a single utterance becomes hard for voice-based assistants. So if you, for example, ask something like, book me a flight from Seattle to New York on Alaska between 24th of December and 5th of January, and make that a round trip. There are just too many fields and too many slots to fill in that sentence, and becomes hard for Alexa to recognize. It becomes easier when you ask for, book me a flight to Seattle, and subsequent turn make that a round trip, book it from 25th December to 4th January. Also, using context around slots help a lot. For example, say you're Amazon, or you're a content provider, and you have audiobooks and movies. Just saying Harry Potter doesn't help disambiguate whether you're talking about the Harry Potter audiobook or you're talking about the Harry Potter movie. And adding context like, I want to watch X, or I want to listen to X, helps us know whether you were talking about an audiobook or were you talking about a movie. So always make sure that there's some context around the slots to help better recognition. Now, how to write great intents? Again, as I said, intents are about one specific action or one specific purpose that your skill wants to do. So split the heterogeneous intents, like split the user profile intent from the flight booking intent or from the car booking intent. Again, wherever possible, use built-in intents as they generalize better and are powered by much more data. Also, what developers told us is it helps if you paraphrase your sentences. Ask your friends about, show your skill to your friends and ask how they would interact with the skill. Or use Mechanical Turks or some good open source paraphrasing tools which can help you rephrase your sentences so that you just get more examples of the way someone might interact with their skill. To conclude my talk, ASK is a service, a tool to connect developers directly to customers on a voice service like Alexa. Developers, the community developers is constantly extending Alexa's capabilities and growing the voice experiences that people can have on Alexa. And as we get more data, we improve the experience by constantly training the models again and improving the performance. And as we build more skills, we make Alexa more intelligent and powerful, and bridging the gap between humans and machine. I'll conclude with that.